Дорогие друзья, dear friends, I'm happy to start our today's seminar, and our speaker is Ivan Dmitrievich Remizov, and he will from Nizhny Novgorod, and he will tell us about Chernoff approximations and solutions to some equations. So we have to share his slides. So I think your slides are here. Yes. The approximation, the speed of Chernoff's approximations for operator semigroups and approximate solutions of differential equations. So Ivan Remizov, and let's welcome.
Thank you for such a kind introduction. Can I please take this seat? Could you please make the slides full screen? Could you please make it full screen? Everything is in Chinese here, so I have some problem with it. This is not full screen.
Oh.
But I think.
Do you have Adobe Acrobat?
Oh, well, I think, well, let's do it. It's okay. It's enough.
It will be difficult for me. Do you have Adobe Acrobat Reader?
No.
No?
Sorry.
Ну ладно. Просто когда слайд действительно можно листать, это очень удобно.
А вот у вас есть курсор? Вот,
а он не сможет листать. Нет. Он именно когда полный экран, на полный экран здесь. А здесь, видите, не полный экран. Ну, то есть мне придется вот так мотать, а это, ну, нет, неудобно.
So
it is not full screen. The full screen mode is the regime when one slide per one screen. Here we have something different from that.
Actually, this
is not full screen.
This is not a fit for the ratio.
But
that's the ratio.
This is not full screen. Full screen, one slide, or this is not about scale. It is anyway not full screen because I'm sliding the next slide like here. If it is full screen, then I just put one button and it goes immediately to the next slide. What are the programs? I'm happy to introduce my talk. In Russian it is «Скорость сходимости черновских аппроксимаций полугрупп операторов и приближенное решение дифференциальных уравнений». In English it will be the rate of convergence of Chernoff approximations to semi-groups of operators and approximate solution of differential equations. The main result of this talk is the theorem obtained with my co-author Oleg Galkin. This theorem gives the estimate for the rate of convergence. Before stating the main theorem, I will provide several definitions, examples, which could be...
What? We should admit people to come. Yeah, you see? Okay. Allow them. Yeah.
Okay, please go. Maybe.
Maybe you can just allow everyone to come.
Okay, no problem. I can.
Well, so the first part of my talk will be kind of a motivating one, where I will give some preliminaries and motivating examples, and in the end I will state our theorem and give a scheme of the proof. Also, I have a poster here, you see. You are welcome to study it and ask questions. Here are results of numerical simulation of the convergence, which I will be speaking about. And we numerically observe some effects which we do not know how to explain theoretically. So those who are interested in differential equations, in operator theory, you are welcome to join this research because here indeed there are some challenging open questions. А что-то перестало работать влево-вправо.
Можно
тыкнуть на экран. Там, наверное, активное окно. Это...
Вы правы, спасибо. So, let me please sketch our today's topic on the map of science. Of course, we deal with mathematics, functional analysis, and even more operator functions and operator exponents. One parameter semigroups of operators and Chernoff approximations of C0 semigroups. And our topic is a subtopic for Chernoff approximations, namely estimates on the rate of convergence of
yeah, but maybe you can draw a flower, how it is related to differential equations, partial differential equations, and many, many areas of mathematics and physics, not only just this nested when it is written as very small, but maybe it's very large in some sense.
Well, I think I'm not ready now to draw the tree of science with all the flowers on that beautiful tree, but I will, of course, give statements that link C0 semigroups to other important mathematical objects. Those who are interested in this topic, you are welcome to start from a very nice overview by Yana Budko on the method of Chernoff approximation. Due to technical difficulties, we started later than expected, and also those slides are actually for 2 lectures. So I will be skipping some slides, and
so at some point you are always welcome to give us your second lecture at some time. We will define when, if you wish. So if you wish, it can be.
Well,
not now.
So please make a decision. I have 2 options. First, proceed slowly, but
yes, better to proceed slowly and then organize some second lecture. It's the best.
But in that case, I will not state the main result.
Well, maybe you can state that with proof.
The statement, well, is so it depends on you. Proceeding fast.
Okay. Yeah.
So okay, it's you who decide.
Yes,
of course, I can.
think yeah. And now let's go slowly because our audience is not mostly is not. So many definitions will be needed.
Yes,
so
and
let's go slowly. Let's go slowly, please.
So I consider this talk as the first part of my mini course given here.
Okay.
Right?
Okay. Maybe a mini course. Yes.
Okay. So. Then we proceed slowly, and today is the first lecture, and the day of the second lecture we will find. As for me, I will be in Moscow 1 more week, then I leave. So probably we should take this into account.
Yes.
Okay, so great. I am about to start from the following question: how to define an exponent of an unbounded linear operator? Before I start, please raise your hands, those who had any course on functional analysis. at least any course. Okay, thank you. Do you know the notion of linear space?
Yes.
Notion of a linear operator in linear space? Norm on the linear space?
Yes.
Norm of a linear operator on a normed linear space? Maybe no. Okay, then I write the definition over here. So suppose that, well, this is a linear space with a norm on the linear space, and we have a mapping, say A, which maps the linear subspace D of A to this F. And D of A is a linear subspace in F, and the norm of A is defined as follows. So we take all the vectors x from the domain of A and calculate AX and then calculate norm of AX divided by the norm of X and take the supremum. If the supremum is finite, then this norm, well, we say that the norm of linear operator is finite, and due to linearity, the condition of having a finite norm for an operator is equivalent to the fact that it is continuous on D of A. And even more is equivalent to the fact that it is uniformly continuous on D of A, because the linearity is a very strong property. So that's it. If every fundamental sequence in F has a limit, then we say that F is a Banach space. And if you know the notion of the scalar product, yes? So and you know the standard formula that allows to define the norm having the scalar product. The formula is the following: square root of the scalar product of the, that's it. And if you have oh, привет, Олег. Привет, Олег. If you have an Euclidean space, which means the space with a scalar product, and it is a Banach space with respect to that norm generated by scalar product, then this Euclidean space is called the Hilbert space. That's it. So, now we know what is the unbounded linear operator. It is the operator which does not have a finite norm. And of course, due to the theorem which I stated before, it is discontinuous. So let us think how we define exponent for a simpler objects. For example, if we have a number, say L, and want to calculate the exponent of L, then this exponent is type of object is a number, and it is defined via this standard power series. No problem with defining exponent of a number. When we want to calculate the exponent of a matrix, it is again easy because it is the same type of object, a matrix, and the same way of definition works this power series. It converges with respect to the norm in the space of all matrices of the same dimension as L. It is not written here, but we'll say if L is n by n matrix, then e to the power L is also n by n matrix, defined as the sum of this series. Even more, if we have infinite dimensional space and bounded linear operator, then it is again easy to use the same way. The type of object of e to the power L is the same as type of object of L. It is bounded linear operator, and the way of defining also the same. This series converges in the space of operators with respect to operator norm. It is easy to prove it using the Cauchy criterion. This number series converges, and hence the.
But here everything is associated. If it
Of course.
Okay.
Yes, of course. Yes. Now, let us think what will happen if L is a more complicated object without a natural finite norm. Then this series diverges, and we have a problem with definition, because, well, how can we understand this power series? So even the domain is smaller, because say the domain of A squared. What of A squared? What is it? It is, and these vectors f from 0 to A such that A f belongs to 0 to A. Yes, so A squared is A f. So first we need f to belong to 0 to A, so we can calculate AF, and then we want to apply A to it. So all that also should belong to 0 to A. So we see here that the domain of A squared is smaller than the domain of A, and if here we have n k going to infinity, the domain becomes smaller and smaller, and well, what we will have as that limit. This is why this way of definition of exponent is not a good way. So when we have here unbounded linear operator, then it is not easy to define e to the power L, because it is not clear which type of object it should be, and equal to what, how we can define it. So this is a challenge, and let me show how can we deal with this challenge. So the possible approach here is to stop the attempts to define e to the power L directly. Instead, we can define e to the power TL as a function of non-negative number t, not as a function of unbounded linear operator. And then we can define e to the power L as e to the power 1 multiplied by L. Here, with that idea, we have now a simple object in the domain of definition. Yeah, non-negative real number. This is a very nice object to define a function of it. And here we should select a type of object which is still not trivial. For example, infinite dimensional, so it can contain all the infinite dimensional complexity, but well, still not so wild. Unbounded linear operator is too wild object, but bounded linear operator still can have all the infinite dimensional complexity, but to be more tame. Okay. So we decided what we will put here and what we will put here. Still, it is not clear what we will put here. How to define it.
Maybe it can be related to the product integration and just solutions of a prime equals to xa, So we can integrate holonomies in differential geometry, just integrate holonomies and solve a usual system of differential equations, and then we will have a family. Then we will have a family, and maybe it can be used in differential geometry, I guess.
That's right, but here I'm not using the notion, well, any geometrical notions, but the idea of using the ordinary differential equation to define the exponent is the right idea. It is exactly what we will do. Well, almost exactly. So, still, it is still difficult to define explicitly the exponent, and to overcome this difficulty, we will consider not e to the power L, but the whole family, e to the power TL, and consider properties of e to the power TL as the function of t that it possesses when L is a simpler object, say number or matrix, and state them, I mean the properties, in the case when L is an unbounded linear operator. So first, we obtain a reasonable definition of e to the power TL, and later search for methods of calculation of e to the power TL. And this leads us to the semi-group as a notion of exponent, and to the Chernoff theorem as a method of calculation of this exponent. Which properties of the exponent we wish to save? Можно мне как-нибудь сесть так, чтобы голову не ломать?
Не знаю, хотите, да, хотите так сказать.
Дотянется? Дотянется? Вот так, да. Даже вот так. Да-да-да, наверное, так получится. Во, отлично. А то просто я боюсь, может быть, Great. What properties of the exponent we wish to say to save? Suppose that t is a number, non-negative real number, and L is a complex or real number. What properties do we have? Well, e to the power 0 equals to 1 for numbers, and if L is a complex or real matrix, then e to the power 0 is the identity matrix. The addition of number is mapped to product of number or of matrices, and function that maps t to e to the power TL is continuous. The derivative with respect to t at 0 is equal to L, and at an arbitrary number t equals to L e to the power TL. Agree? Yeah. Exponent indeed has all these properties, and let us modify these properties in such a way that they will hold when L is a linear operator, probably unbounded linear operator in some Banach space F. But keep in mind that these properties must hold in the form that is given above here when L is also a number or a matrix. If our
so number 4 is exactly what I was talking about.
Yeah. And you will even see the Cauchy problem for ordinary differential equation that you mentioned. So when our Banach space F is the space of real numbers, then linear operators are also real numbers that act as multiplication by this number. So all these cases are particular cases of Banach spaces. in that two cases, L is a number. In these two cases, L is a matrix. Okay, so this will lead us to the notion of C0 semigroup. That's it. By definition, C0 semigroup is parameterized by a number T, family of linear bounded operators V of T in Banach space F. If and only if for each F small from F curly, all conditions hold. First condition, that for every vector F, V0 of F is equal to F. So V of 0 is the identity operator in Banach space F. Addition of numbers again maps to composition of operators. And this is called the semigroup property. And for every fixed vector F, V of T F continuously depends on T. And this is called the strong continuity condition. Why strong continuity? Because for each T, we have some linear operator V of T. We can consider the space of linear bounded operators in Banach space F. And there is some several standard topologies on the space of linear bounded operator in Banach space. One of them is the standard norm topology generated by this norm. Indeed, the space of all linear bounded operators in Banach space is a Banach space with respect to that norm. And we can consider continuity in that norm. But there are several more topologies, and one of them is the so-called strong operator topology. And continuity in that topology is equivalent to this property. This is why this, say, vector-wise continuity is called the strong continuity condition. So altogether, we have a strongly continuous one parameter semigroup of operators. I should mention that here we use algebraic terminology, the semigroup, and from the algebraic point of view, these objects are not interesting because the algebraic structure of all objects, of all operators that can be represented as V of T for some T is not interesting. It is what is interesting is the analytical point of view. We are interested which particular number T goes to which particular operator V of T. So here you see we use round brackets, meaning that this denotes not the set of all operators that can be represented as V of T, but we are interested in the whole function V, which maps T to V of T. Questions?
I think that it is maybe very similar to the space, topology space. We have space.
Lie space?
Lie groups.
No, you can think that C0 semigroup is a continuous representation of the semigroup of non-negative real numbers with addition. But we are not interested in any Lie structure here.
Yeah, actually, when we think about the B group, and maybe it is comes from the geodesic. It's use flow.
Yes, indeed, yes.
Differential geometry is one of just
Yes, there's
so
that
their area of research, they are into them differential geometry.
so when L is a differential operator on manifold, then you have this geodetic map, and this is the exponent.
This is the infinite dimension of space.
Yes, 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 yes. Okay. No, now let me introduce the notion of the infinitesimal generator of the C0 semigroup. In algebra, we have algebraic generators, but this is something different. It's an infinitesimal generator. First, we define the following set, D of L. D of L is a set of vectors F for which the following limit exists. And as V of 0 is equal to identity, you can write here V of 0. And what you have here, V of t minus V of 0 divided by t applied to F. So this is the derivative at 0.
So roughly speaking, this is the space of derivatives. The space of possible derivatives.
Of the domain. Of the domain. So we consider this V of Tf as a function of two variables T and F, and select all the vectors F such that this function is differentiable in T at 0.
Okay.
Probably is necessarily a subspace.
Of course, yes. Operator V is linear operator, and the limit is linear operator. So indeed, D of L is a linear subspace in F. Why? Because if we take F equal to 0, then everything here is 0, so 0 belongs to D of L. And if we multiply F by, say, number alpha, then alpha goes here and then here. So, and the addition also works well here. So it is obvious that, almost obvious that D of L is a linear subspace in F. It is less obvious, but still follows from the definition of C0 semigroup that it is a dense linear subspace.
Dense in the whole space.
Yes, dense in F.
How does it fall just on continuous?
Because here we have here a composition and continuity, and composition is a strong property. This is some fact from functional analysis, which is not actually important here, so I will skip it. But still, so the semigroup axioms are so nice that D of L appears to be a dense linear subspace, and we can define then operator L as follows as the value of this limit. And it is natural to use notation that LF equal to V prime of 0 applied to F. That's it. Then, again, from axioms, the following, and from this definition, the following theorem follows. For each C0 semigroup, V of T, the infinitesimal generator L exists and is unique. Well, and defined by this notation directly from the semigroup. And the following notation is used. V of t equals to e to the power tl. Then the generator defines the semigroup uniquely, which means that if generators are different, then for some number t, the exponents also will be different. As I already said, that the generator is densely defined on DFL and closed linear operator. What does it mean? closed operator. It means that the graph of operator is closed when considered as a linear subspace in the Cartesian product of f and f. And here again, we don't see the bottom line. Let us again try to make it better. Oh, perfect. Now it is perfect. Great. So, and the generator satisfies the following equation. It is written here d by dt, e to the power TLF equals to L e to the power TLF for all f from the domain of L. And as you can see, these are exactly these are properties. This is the definition of the generator. This is the property. We have also continuity and all these conditions. So we indeed managed to define the exponent of unbounded operator in such a way that that this definition works also when L is a number or is a matrix. This property is a corollary of the composition property. Let me show it. Suppose we want to find some that stuff for some t. This is a limit when say epsilon tends to 0. V t plus epsilon f minus f divided by epsilon, and then we know by the composition properties that this thing is equal to v of t, v of epsilon. So we have limit epsilon tends to 0, v of epsilon v of t divided by epsilon, and v of t is a linear bounded operator. So it is a continuous function. And we can take v of t first here, and then here, and then under the sign of limit, we will have v prime of 0 here.
But however, so-called derivative with the very more complicated name than all our lives can be not bound, can be unbound. Yes, it's still capital.
I didn't got the question.
Even what?
I didn't got the question.
Okay.
What is the question?
So,
is this clear?
Yes, so I just understood that v of t should be bounded and L capital
is not.
necessarily.
Yes, indeed. Yes, that's right. That's it. So here, C0 CB group is a family of linear bounded operators. As before, here I would like the exponent to be a linear bounded operator. But well, still we need to define it somehow. What we have now, we know that for every C0 CB group is an exponent of some operator, which can be easily calculated from the semi group. But there are two more questions. First question, for what class of operators the semi group indeed exists? So describe the class of operators that can generate semigroups. This is not an easy question, and the answer is given by Helia-Sida theorem and Helia-Sida-Meyer-Phillips theorem, which I would prefer not to touch today. But I mentioned that, of course, every generator is a densely defined closed operator, but not every densely defined closed operator indeed generates some semigroup. So we defined an exponent from unbounded linear operator, but not from every linear unbounded operator, only from those operators that are generators of C0 semigroups.
Subspace between bounded ones and all ones. We don't know what is this medium subspace of the operators. For those, we can define with so-called exponents.
Well, actually, the set of such operators doesn't have a natural structure to call it space.
Is it not a subspace? Maybe I confused if I created.
Helia-Sida theorem is stated in the terms of the resultants of those operators. Okay. So we know how to calculate the exponent from some unbounded operators. That's already nice. Now, let me give some terminology overview. These names are used as synonyms, C0 semigroup and strongly continuous one-parameter semigroup of linear bounded operators and Banach space, full synonyms. This one is shorter, so it is used more frequently. There is a more general object, evolution semigroup. In that case, operator V of t is allowed to be not linear. And there are several...
Maybe instead of exponent, you can change your... t over dt is not constant. So it is not always the same, but different.
That it is even exactly this case. When we that's different case. Now, what is written here? Operator V of t is allowed to be not linear. It is called evolution semigroup. What you mentioned when say L is not constant, yeah, but depends on t also. This is called evolution family, and it is not listed here.
Okay.
You consider the case when this ODE, Cauchy problem for ODE, has time-dependent operator L.
Yes.
Still has a unique solution, but the operator is time-dependent. So this is called evolution family, not listed here, but that's interesting object indeed. So we have positive semigroups in which operators V of t must be positive, and even there is a scientific journal called Positivity, which is related in particular to positive semigroups. There are quantum dynamical semigroups and quantum Markov dynamical semigroups that are important for quantum information theory. Time evolution operator for Schrödinger equation is a C0 group of unitary operators. Also, evolution differential equations, stochastic evolution differential equations are closely related to C0 semigroups. There is an interesting object, V continuous semigroups. It is a semigroup which is continuous in some sense close to C0, but not exactly that. in B continuous semi-groups, we substitute the last condition with some other more complicated condition, but this object, B continuous semi-groups, has nice applications. And actually, C0 semi-groups are connected with many objects in the fields of mathematics and physics, where evolution in time is important, because the number t, which we have here, naturally can be interpreted as time. So here is the Cauchy problem you mentioned. I would like to say a few words on the connection of C0 semigroups and dynamical systems. First of all, C0 semigroup is a linear autonomous dynamical system, just directly. This Cauchy problem for ordinary differential equation in Banach space has a unique continuous and differential solution U given by the semigroup. That's it. Let us check it. If we put 0 here, then U of 0 equals to e to the power 0, which is identity, equals U0. This condition holds. And this condition directly follows from this condition. It is almost the same. That's it. Even more, we can, for that Cauchy problem for differential equation, we can rewrite it as an integral equation, and solutions of that integral equations are called mild solutions of that Cauchy problem. Here in differential form, solution exists for all U0 from the domain of L, because here we apply L to U, and if you want to apply L to U of 0, then U0 should be from the domain of L. But when you write integral equation, then the solution exists for all U0 from Banach space F, and they are called mild solutions to this Cauchy problem. And again, this solution is given again by the same formula, this formula. So we have a dynamical system in Banach space F. This is the initial state, and this is the evolution law, and this is the time evolution operator. That's it. Exactly as when this Banach space F is a space of all real numbers. Exactly that. And the formula is exactly that, just from elementary course of ordinary differential equations. Agree? Yeah? Next, I would like to consider the particular case, the Schrödinger equation. From my point of view, this is my personal point of view, C0 semigroups theory was indeed took an essential place in the whole picture of science after this theorem. Marshall Stone, American mathematician, in 1932 published his theorem in Annals of Mathematics, and the theorem says the following. Suppose F is a Hilbert space over the field of complex numbers, then there is a one-to-one correspondence between self-adjoint operators in that Hilbert space and one parameter C0 groups of unitary operators V of t. And the correspondence, this correspondence is given by the formula V of t is equal to e to the power ith. So the generator of one parameter C0 group of unitary operators has always the following form: I imaginary unit multiplied by some self-adjoint operator, and vice versa. For any self-adjoint operator in Hilbert space, even unbounded operator, there exists an exponent. And exponent is not only the semi-group, but C0 group. This means that T can be negative, and V of minus T is equal to V of T inverse. Well, and unitary operators, you know what is unitary operator. Yes? Good. The following theorem has the following corollary. The Cauchy problem for the Schrödinger equation, here H is a self-adjoint operator in Hilbert space F. Psi 0 is vector from Hilbert space F. These vectors are called pure states of quantum system, and H is called the quantum Hamiltonian of the quantum system. This H is a Planck constant, some small positive constant. This is imaginary unit. And this is called the Schrödinger equation, that equation. And the solution by the previous reasoning and by the Stone theorem is given by the following exponent. And it exists for every psi 0 from our Banach space. So, Stone's theorem is a fundamental mathematical fact which lies in the base of quantum mechanics. It states that every quantum system with arbitrary self-adjoint Hamiltonian has time evolution from every state, because Schrödinger's equation has a unique solution for each psi 0 given by this formula. Stone's theorem established the existence of dynamics for every quantum system. So this is a very basic fact of quantum theory, and even more, the norm of psi of t is equal to norm of psi 0, because the norm of time evolution operator here, the norm is equal to 1 because it is a unitary operator, thanks to the Stone theorem again. And as we have a C0 group, then we can take inverse. I already said that V of minus t is equal to V of t inverse. That's it. Questions? А вы записываете вот эту штуку вот сюда, чтобы лучше запомнить?
Ну, окей, люблю брать.
Это здорово. Я выслал, кстати, слайды.
Да. Мы можем куда-нибудь выложить.
Да, вы можете куда-нибудь выложить, если хотите, для тех, кто не делал конспект. Так. Well, C0 semigroup may describe some linear non-autonomous dynamical systems. For example, if we take the previous Cauchy problem and add here some time-dependent vector f, then this Cauchy problem has the following unique solution. And you see that this formula is pretty close to the formula for variation of constants for ordinary differential equations. These are equations in Banach space.
Okay.
Well, and what about nonlinearity? Surprisingly, nonlinear dynamical systems on nonlinear spaces, for example, manifolds, metric spaces, may be interpreted as C0 semigroups. Let me show how this works. Probably this will be insightful for you. The connection of C0 semigroups and semiflows. Do you know the notion of semiflow? No?
I don't know.
Then I will just skip this slide because
Then you have shown that B L, right?
потоки, полупотоки, непрерывно динамические системы.
Ну, поток понятно.
Про это
но
сказать или не надо?
лучше сказать.
Ладно. Окей. I will then, there is actually a definition here. So theorem says the following. Informally, it says that semi-flow in metric space naturally defines a specific type of C0 semigroups in some space of functions on this metric space. Let the statement of the theorem, let M be a metric space and F be the set of all real-valued, uniformly continuous and bounded functions on that metric space. Real-valued functions on M, uniformly continuous and bounded. It is a Banach space of all uniformly continuous and bounded functions M, F, defined on M takes values in F, with a uniform norm, also called sup norm, Chebyshev norm, that's it. Suppose that phi small is a semi-flow with the following notion of continuity. What is it? The semi-flow? It is a function phi defined on the real semi-line multiplied by the Cartesian product with the manifold M. And it has the following properties. Phi x equals x from M, and phi of T1 phi of T2 equals to phi of plus 2x, also for all x.
Well, it's like a mention of the non-negative minority on this main.
Yes, yes, but again, it is not the algebraic structure here is interesting because it is more or less trivial. The analytic structure.
So there should be T1 and T2 somewhere on the left side.
Yes, here T2.
Yeah, okay.
Thing. That's it. So the composition law. And this mapping, which maps to T to psi of Tx, is called the trajectory of a dynamical system, which starts at x.
Was is very actively anti-writing piece, very actively studied by heads of our former faculty, chair of department, former university.
In the formal life.
Everything is relative.
So-
Just 10 years ago.
Like, yes, you're right. 10 years ago, you're right.
Still short.
Um,
I really like this job.
So you like here more, yes?
Not simply more, but incompatible more. There are distant orders of comparison. Of course.
Okay, I have never been a professor here, so I don't know.
I'm also just an associate
But
professor.
nevertheless, so you teach here, so you have better students.
But sometimes there is a converse effect, or a certain, at least two effects. Even effect of two effects is quite much. So,
Two actors?
say, USSR, Russia, so effect of one act, but if there is some other kind, there is a theater of two actors, and somebody can guess what I say in the next sentence before I say it. It underestimates my story.
So here you have someone to talk with.
In this term, I think no, but this time, last time here, most full explain. But of course, not complete.
Okay, let us proceed.
Okay.
Phi is a semi-flow on M, which means that this condition holds, and phi has the following notion of continuity. First, this mapping that maps x to phi of tx is uniformly continuous in x for each t. And second, this mapping that maps t to phi of tx is continuous in t uniformly with respect to x, which means, well, that this limit of this supremum equals to 0. So continuous in t, continuous in x. Then let us define phi capital as again the function of two variables. Phi small is a function of two variables. First variable is a non-negative number. Second variable is from manifold. Here again we have first variable non-negative number, and second from the Banach space of real valid functions on manifold. And we define this phi capital by the following rule. Phi of t and f is a vector from here, from f capital, so it is a function on M. That means that for all x and then it has some value, and this value is defined as f of phi small of t and x. What does it mean? It means that I have a dynamical system, phi small, and I define a shift through the trajectories of that dynamical system. I can give you, so yes, you're welcome, of course, to photo this, and also I can give you the full poster if you like. I mean, electronic copy of this. So there are indeed here open problems here, and everyone is welcome to solve these puzzles. Probably this is the most complicated thing in the whole Chernoff approximations theory, at least for me. So here is the conditions of the theorem, and here is the implication of the theorem. Let us define operator for each t, define the operator q of t by this rule. Its value on vector f is equal to that capital of t and f. Then this is a linear bounded operator in F, which is actually easy to see. I have a dynamical system phi in manifold, continuous dynamical system, and I define a continuous dynamical system in the space of functions, of real valued functions on manifold, defined by this equality.
Okay.
So I make change of variables as shift through the trajectories of this continuous dynamical system. And this phi used to define operator Q of t, and it appears to be linear bounded operator in that Banach space, and even more to be a contraction semi-group in F. Contraction, that means that the norm is less or equal than 1. If this is a reversible dynamical system, not a semi-flow, but flow, then this will be not a semi-group, but group, and those operators will be unitary. This phi capital is called the Koopman composition operator after Bernard Koopman, who introduced it and used it. And what we say here, so non-linear dynamical system, the semi-flow phi small, is interpreted as linear dynamical system, C0 semi-group, phi capital. So we pass from non-linear dynamical system to linear dynamical system, but it is infinite dimensional. We have also some other procedures which allows us to pass from non-linear to linear. For example, we can make standard linearization of dynamical system near some point, and then we will again go from non-linear dynamical system to linear dynamical system, but locally. This is called linearization. Also, we have quantization. When we have some non-linear Hamiltonian mechanical system, then we make its quantum analog and have the corresponding Schrödinger equation. And quantum system is linear. So again, quantization is a way to pass from non-linear system to linear system, but again, infinite dimensional. And together with linearization and quantization, this procedure described by this theorem is called Koopmanization. And it was very popular, so jokingly sometimes called Koopmania.
I think it's Koopman, and Koopman, it's the Dutch version of Kaufman. Yeah, Koopman. Yeah, it's
Probably
Dutch.
But with double O.
Yeah, with double O. Yes, in Dutch it's with double O. It's
but we don't know which language is used here because it uses Latin letters. So I don't know. I have not met that guy or his students or colleagues. So in Russian.
There is a Jewish surname here. In Russian here, I knew such a paper.
Yes, of course, I also know. So actually, I don't know. If you know that guy, then let it he be Kaufman.
Excuse me, I think we have 15 minutes for this.
Yes, but we decided that this will be only the second part. So, and I will not state the main result, but give some slow introduction that everything will be clear. Is everything clear?
More or less.
More or less? Okay. Do you have questions on this theory? It is not the main part of the talk. Just I would like to mention that nonlinear dynamical systems can be understood as C0 semigroups. So C0 semigroups are so nice that they include even nonlinear dynamical systems. And this is the way how they can include. Okay? Okay, so we know that semigroups are so useful. So what? Suppose that we know the semigroup e to the power TL with generator L. What concrete equations with operator L in Banach space we can solve with this knowledge? These are 4 equations. The first is the Cauchy problem that we already discussed. The second is the Cauchy problem that we already discussed. They are differential equations. The second is the following integral equation that we also already discussed. And the last, the fourth item of this theorem is about a solution of this algebraic equation. This theorem is a collection of well-known results of C0 semigroup theory. If we know the semigroup with generator A, then we can solve these 4 equations. Actually, much more than 4, but I focus only on that 4. So let me stress the last condition. Suppose the semigroup e to the power Ta with generator A satisfies that condition. For every semigroup, such constants M and W exists. I use them here just to fix the notation. And this, if this condition holds for all t, then for each lambda with real part greater than w, and for each vector j from our Banach space, this equation has a solution f from d of a, and this solution is unique and in d of a, and is given by the formula f here. It is overlapped by this unpleasant thing, but it is written f here, f small. It is equal to the resolvent of operator A calculated at number lambda. Well, indeed, what we need to solve this equation, suppose A is a number. Then we take lambda minus A multiplied by f equal to g. And then we take the inverse to lambda minus A and apply it to the left and the right part of this equation. So f is equal to lambda minus A inverse applied to j. And indeed, this is called the resolvent of operator A calculated at point lambda. And there is a result in C0 semigroup theory that the resolvent of generator of C0 semigroup is the Laplace transform of the semigroup. Indeed, for example, imagine that A again is a real number, lambda is a real number. Then this integral is easy to calculate, and it will be equal to 1 divided by lambda minus A. That's it. Questions? Is it clear? Of course, I'm not giving the proofs, so it is not exactly clear, but the statements are clear.
I think so.
Questions?
Well, I don't think so.
No questions. Okay. And I have like 5 more minutes. Yes?
I think so, yes.
So we discussed Cauchy problems and equations in Banach space, but we can solve actually partial differential equations for number-valued functions of number-valued variables, and even can solve ordinary differential equations. Let me consider example. So this will be the last example today. Consider functions f that maps real numbers to real numbers that are uniformly continuous and bounded, and denote the space of all that functions UCB of R. It is a Banach space with a so-called uniform norm, subnorm, and suppose that functions a, b, and c belong to UCB of R, to our Banach space. Suppose that they are some known parameters and define operator A capital by the following rule. So it is a second order linear differential equation, differential operator with variable coefficients A, B, and C. Suppose A d of A is a closed linear operator with the domain d of A, and suppose it generates a C0 semigroup. We define first A on the space UCB2. This is a space of all functions f, that f, f prime, and f double prime belong to UCB.
So no approximation so far. No Chernoff approximation.
No Chernoff approximation so far.
Okay.
Just explaining why semigroups are indeed needed to be approximated, that they are indeed interesting, that they deserve approximations. Here, the example is the following, that C0 semigroup with this generator allows to solve these two equations, this parabolic equation and this ordinary equation. How we can do it? We first define this operator A on the UCB2, and then we make the closure of the graph of that operator, and the operator of this new graph, we say that it is A. Consider the following Cauchy problem for parabolic partial differential equation. It is the equation for function u small of t and x, and I introduce function u capital of t, which takes values in our Banach space. Probably this one is the most important thing here, that I have a Cauchy problem for partial differential equation. It is for function u, real valid function, and I make here the Banach valued function u capital by this rule. U capital of t is u small of t dot, where dot is the omitted argument. So ut is the function of x that maps x to the value u small of t and x. Is this clear? So the function of two variables, u small of two variables t and x, for fixed first argument t becomes a function of one variable x, and it belongs to that space UCB of R. So this Cauchy problem for parabolic partial differential equation is exactly this one Cauchy problem for ordinary differential equations in Banach space with exactly this operator A, because it's here the derivative, second derivative, first derivative. Is this clear?
Excuse me, you speak this second order linear PDE have a solution. In which sense of the solution?
In the most classical sense, that means that all the derivatives exist in.
Not only the weak.
No. And also the following ordinary differential equation again has a solution given by this Laplace transform from the semigroup. Here I must stop, but I will at least show something related to Chernoff approximations. Here is the second example, and here is the Chernoff theorem, and this differential operator admits this Chernoff function and that Chernoff function, and that ODE can be solved using this Chernoff function, and the solution is given by this formula. And this formula was highly circulated in the mass media, thanks to the news making facility of Higher School of Economics, and I was overtired by saying that this is a nice result, but not something great, and so on. That's it. So here I must stop due to the time limitation. Next, there are some other Chernoff functions, some discussion on speed of convergence, then our theorem, and then a scheme of the proof of the theorem, and after all, my context, and after all, some advertisement of this contest of the diploma thesis of Russian mathematicians. Everyone, please participate. Make a photo of it, of this QR code, and propose your
references. I saw that the young
So I finished. Thank you for your attention. And next time I will show other slides which I just briefly skipped today.
Okay, thank you very much for a nice talk. Are there any questions?
Yeah, I have a couple questions. So, I just
Oh, 这个啊。老师，那我们是不是可以暂停了？可以 stop the recording，停止，然后那个是重新再录制。